Hello and welcome to the next episode in our GPU series. This episode will focus on how memory, and more specifically how DRAM memory works, and why should we care about such low-level details as GPU programmers. Without further ado, let's jump in. To understand how memory works, we have to go into electronic component level of details, and we'll start with the transistor. The transistor has three entry points: the base, the drain, and the source. Let's also add in some input line and output line. In this state, the transistor is blocked, and if we put in some voltage on the input, it won't be able to pass through the transistor and get to the output. But if we also put the voltage on the base of the transistor, it starts being open and voltage can now pass through to the output. If we turn off the voltage from the base, the transistor turns off, and once again voltage can no longer pass through it. The second component that we need to know about is the capacitor, and for simplicity we'll assume that it's always connected to the ground. We can use the capacitor to store charge. What this means is that if we put voltage on its input, it starts accumulating charge, and when we plug it back in, it slowly discharges. With that in mind, we can combine those two elements and create a simple memory cell. When we open our transistor and put some voltage on the source, we can charge our capacitor and store a 1. If we now disable the transistor, the voltage that was stored in the capacitor has no route of escape, so it just stays there holding our value of 1. And if we want to read it, we just open our transistor again. Those memory cells are arranged in a rectangular grid called a memory array. The bases of each transistors are connected using word lines, the outputs are connected to the bit lines, the word lines are being controlled by a row decoder, the bit lines are connected to the sense amplifiers, and those sense amplifiers are controlled by a column decoder. Finally, everything is connected to the data input and output line. Now that we have our memory array constructed, we need a way to control it. And we do that through address lines. Some that represent the row that we want to access, and some that represent the columns. With all of the elements in place, we can now see how to read a value from our memory array. The first step is the pre-charging step, where we put some voltage on our bit lines that is non-zero, but lower than the voltage stored in our transistors. Then, we need to provide the address of the memory that we want to access. The high part of the address goes to the row decoder that decodes it and activates a whole row of transistors. If a memory cell was storing a value of 1, it starts discharging into the bit line, increasing its voltage. Likewise, if the memory cell stored a 0, it starts draining from the bit line, decreasing its voltage. This happens for all of the transistors in a row. Now, sense amplifiers come into play. Their job is to detect the voltage on the bit lines. If it's higher than expected, they load the values of 1, and if it's lower, they load a 0. The amount of data that was loaded to our sense amplifiers is called a page size, and it's usually in the range of 1 to 4 kilobytes. Now that the values are loaded into the sense amplifiers, we can put the remaining half of the address onto our column decoder. It decodes the address of the value that we want to access and passes it onto the data output line. You might have noticed that it's a lot of work, but it starts getting even worse, because after reading the values, our memory cells either lost some of their charge or gained an unnecessary charge. So now we have to write the raw values from our sense amplifiers back to the memory cells. When we want to access our memory again, and we want to get a value that is in a different row than our previous access, we come to a very problematic situation called a row miss. we have to go to the whole process again, pre-charging the bit lines, decoding the row address, reading into the sense amplifiers, and decoding the column address. Luckily for us, we can also have an opposite situation, which is a row hit, where we try to access a value in a row that is already loaded into our sense amplifiers. We can now skip all of these steps that were required when we needed to change the row stored in the sense amplifiers, and just decode the column address and pass the value to our data output line. And the memory kinda does that for you. During the time of writing the rows back to memory, it just outputs a few next values from the row. This is called a DRAM burst, and the amount of bytes that get returned from the burst is a burst length or a burst size. Because of that, and because of the way cache works, memory is accessed in segments, where one segment consists of 32 bytes. When we make a memory access, a whole warp generates a memory transaction that can either be a 32-byte transaction, a 64-byte transaction, or a 128-byte transaction. The transaction size depends on the architecture of the GPU we are using and the type of memory we are accessing. For example, requests to the L1 cache use 128-byte segments, while requests from L1 to L2 are made in 32-byte segments. Also, our accesses need to be aligned to those segments. For example, if we want to access even just 2 bytes that are in 2 different segments, we still need to load both of those segments into memory. This brings us to the crux of the problem. What does that mean to us as programmers? To answer this, we can examine a simple offset copy kernel. In this kernel, if we look at what the whole warp is doing, it is accessing 128 bytes of memory with an offset. We run this kernel and measure the timing for different values of the offset variable. Note that on the graph the offset is given in bytes. And if we examine the results, we can see that the kernel performs best when the offset is a multiple of 128 bytes. And this is the memory transaction size when accessing data through the L1 cache on my architecture. Another kernel that we can examine is the strided copy kernel. All it does is just copying from one buffer to another, but we can specify the stride between successive memory accesses. So, when we are using a stride of 1, we access memory regions that are next to each other. With a stride of 2, they are separated by 1 value, and with a stride of 4, each access is 4 values away from the previous one. We can run this kernel for different stride values to see how this affects the speed of our algorithm. And as expected, the bigger our stride, the longer it takes to access our memory. But there are 2 points that are standing out, where we have big increases followed by plateaus. One is 128 bytes, which is the segment size of one memory request going through L1 cache. And the next one is at 1 kilobytes. And this is the page size, so the amount of values that get loaded into sense amplifiers when we select a row. We've come to the end of another episode, and another episode related to memory. By now you should see how crucial efficient memory management is if we want to get the best performance out of our GPUs. I'm hosting a Buy Me a Coffee for those that want to support this channel. A shoutout to Alex, Udit Ransaria, forgive me if I mispronounced it, and 3 anonymous donors that supported so far. But you can always support me for free by subscribing, leaving a like, commenting and sharing this video with your friends. I'll see you in the next episode. Bye.